Hello there, I'm Shoumik Bhattacharjee from Team Joatali and welcome to the presentation on Screen Space Ambient Occlusion. Let's begin. First, let's talk about ambient light. Ambient means surroundings. We have heard about it in Phong illumination model. If we only consider the other two components, that is diffusion and specular light, we find this image, which is very dark because we're only shooting rays, one ray for each pixel, and as for reflection, we're only reflecting it once, but in reality, light spreads everywhere in an infinite amount, and whenever a light appears on an object, it diffuses everywhere because of the roughness of the surface. So, if we have to calculate the color of a point, we'll have to consider all possible rays that are coming on from all possible direction, but it's impossible because we cannot actually calculate this many rays, which is since our model is using very few rays, naturally it becomes very dark. Now, how are we going to solve it? We'll somehow have to approximate this infinite amount of light. So what we can do is add this hard-coded value to our image, and this is what we get: a very realistic image. This is what we call an ambient light, the approximation of all possible lights around the objects. Now, let's talk about ambient occlusion. Occlusion means obstruction. Suppose this image uses ambient light, but this one looks a little bit more realistic than the previous one because it has shadows in these clefts and cuts. So if we reduce ambient light in this portion, we can get a fairly more realistic image than only using ambient light. The motivation is, as we have seen before, light comes from all possible direction, but if there is an obstruction like this one, light cannot come from this direction, so naturally less light will appear here, make this portion darker. Like in this corner, less light will appear and this place becomes dark. This is what we call ambient occlusion. Now, screen space ambient occlusion. It's simple. After projection transformation, we turn 3D space into a 2D one, and all we have to do is apply ambient occlusion into this 2D space instead of 3D, making our computation way more simpler and making ambient occlusion feasible. This is why it's called screen space ambient occlusion.
Hello, I'm Akanta from Team Joatali. I'm going to explain the screen space ambient occlusion algorithm. So from our Phong illumination model, we know we shoot a ray from the eye to some different frame of the screen for a particular ray which has been intersected in the nearest object. That intersected point illuminated value in three category: ambient, diffuse, and some specular, will be total multiplied by some factor, and then that color will be replaced when we back propagate the ray to the up to the screen. We got a frame color. So what's the gap in this problem? What's the gap in this Phong illumination model is that in our Phong illumination model, the factor IA has been calculated as some constant value which will be taken from our object directly, but it can be seen that the object can be surrounded with some edge, with some object, or that point can be in some shaded value, so some realistic value needs to be put. So to do so, we will use some approximation technique, and to reduce our time complexity or some calculation complexity, we will not calculate in our 3D space. We will calculate this in our screen space, basically in 2D space. At first, whenever we whenever we shoot ray for each frame in the screen space, uh, for each frame we will store two value in two different buffer. One is the depth buffer and another is our normal buffer. Because we will calculate the IA factor from this screen space rather than the 3D space. So only in one iteration we will calculate for each frame this two value, then we will update this value according to this screen space. How this value has been put in this frame buffer? So we can consider this example. This has been a frame. This we have shoot, or the array has been shoot, so that it can intersect in this frame, and we forecast this ray so that it can intersect in our nearest object. From this nearest object intersected point, we will calculate its z value, which is basically the distance from this screen, and we will calculate a normal value which will be directed to the surface normal of this object, and these two value will be put in our this two buffer. These buffers are a 2D buffer. Basically xy represents this 2D grid point. So now in one iteration, or in our first step, we calculate for every frame the z value and our n value. The next term, when we have calculated for each frame, now we will start our next calculation, that is how these frames has been stored with this z and n value. Now we will consider how this value can be updated with our realistic ambient color. At first we will see how this frame value, one's frame value will be back propagated in our object. Then we will see the normal value. By choosing the direction vector normal, we will consider a hemisphere of random radius. Obviously it will be directed in the normal buffer's value. That's why we will store the value in our normal buffer, and we will consider some sample points from this hemisphere. Because of choosing these sample points are really very simple. Now we will consider how these sample points are being projected in the screen. Every sample points are being projected in the screen, and when they have projected in the screen, we will see which frame it has intersected. As before, we have stored the z value for each frame. Now we will compare when they intersected, that frame's z is nearer, or this point's z value is nearer. If we calculated some points that are being nearer, they are called some occluded samples. So we will calculate some occlusion factor, which will be now introduced in our IA as A times IA. Our IA will be some new IA prime, which will be AO times IA. AO will be calculated by these rules, which is some occluded samples divided by some total samples. So by this we will have some realistic ambient color. But there is a catch. The catch is when we will consider for each frame, then we will mapping this object's point. We are doing some uniform sampling. we are not changing these points value from this hemisphere relatively. That's why it can cause something problem as bending problem. We can see this here, circulating bending problem. So now what we will introduce to solve this problem is, we rather than some uniform sampling, the hemisphere part will be randomized at some different direction for each frame, then the problem will be solved. But again, whenever we add some noise to rotate this hemisphere, this will cause some problem. This will be some adding noise in our situation. So now how can we solve this noise to this object's nearer point? Then we will calculate the similar Z value, which frame has the similar Z value. We will take.
Okay, I am Tusher. Let's look at the shader implementation. The process starts by setting up an pixels informations. Get the pixel distance from the camera, which is called depth. Using the depth, we can reconstruct the pixels 3D coordinates. We also need the surface orientation or normal. We then initialize a variable to count occluded samples. The main part of the process involves sampling surrounding the points. We loop a number of times based on our sample count. In each loop, we create a test point by adding a sample from hemisphere to our current pixels positions. We then project this test point to our screen space. To determine the occlusion, we compare depths. We get the sample's depth from the depth buffer. We also calculate the actual depth of the test point. If the actual depth is greater than the sample's depth plus bias, we count it as an occlusion. Finally, we calculate the light factor. Now let's address some common issues and their solutions. At first, self-occlusion. This is when objects incorrectly occlude themselves. A solution is to use a bias adjustment, which slightly offsets the samples. Adding a bias helps to remove the self-occlusion. Then bending. This refers to visual patterns that appear from sampling. This can be fixed by using a noise texture to randomize this sampling. Halos. These are the bright edges that appear around objects. Blur pass can smooth the final result and help with halos. Performance. Many texture samples are required, which can impact performance. We can use fewer samples or caching. Properly tuning the parameters is crucial for good results. Here are some key parameters: radius, bias, and kernel size. Low radius gives a weak effect and can cause artifacts, while a high radius leads to blurry results. If the bias is too low, you can get the surface artifacts. But if it's too high, the appearance will be washed out. A recommended bias range is 0.001 to 0.05. A small kernel size results in a noisy output, while the large kernel size can lead to slower performance. An optimal kernel size gives clean results. Here, this is with self-occlusion, and this one is removing self-occlusion with adding bias, and the surface becomes more realistic. With optimal kernel size, you can find the real difference in the edges of the block. It becomes more realistic in the edges. Finally, the overall limitation. The technique can suffer from screen space artifacts such as disocclusion problems and missing geometry information. There is also a performance impact with the shader potentiality that taking 2 to 5 milliseconds per frame at 1080p resolution. The noise produced by the sample requires careful blurring to mitigate. These artifacts can often be reduced with techniques like multi-view rendering, hybrid methods combining screen space and voxel-based or rate data, adaptive sampling, temporal filtering, or hybrid rendering. That's all. Thank you.